Hello, it's James here. This is part 2 of the OpenDog project, which is an open source dog robot project. It's going to be pretty big, about 900mm long and stands about 600mm tall, so about the same size as Boston Dynamics Spot Mini robot, but not quite as good as that because I'm not as good as Boston Dynamics. So last time we looked at the overall design in CAD, we looked at some code, and we looked at the O-Drive Robotics brushless motor driver. So this robot is going to have 12 brushless motors and encoders on them and ball screws, and it's going to be made of metal that I'm going to CNC, and some 3D printed parts, and some extrusion and all sorts of stuff like that. So this time we're actually going to delve into that design a bit more in one leg. We're going to look at some of those detail parts of actual metal and mechanics and things like that, and we're going to try and make one knee joint. Then we're going to look at the code again and check that we can control it before we go and buy all of those motors, even though I've already bought lots of them, and all of the motor drivers and all the other stuff. Then after that we can pretty much get on and build it. So here's the CAD I drew last time, which I published, and you can find the link to my GitHub in the description to get this CAD and the CAD and code from this episode as well. But this time we're actually going to concentrate on one leg, so I've built these joints that work. So the basic aim is we've got this brushless motor driving a ball screw, a bit like the way we did the exosuit, and obviously that's going to move the leg, and we work out the trigonometry to work out the inverse kinematic model that I explained last time, so we can calculate the joint angles, and essentially that's how it's all going to hang together. But I drew this CAD in quite a crude way, so I mean the ball screw is there and it's roughly the right size, but actually looking at the physical parts, some of these blocks are different shapes. This is a T-slot extrusion, and I really wanted a wheel that ran up and down that. So I need to change the placement slightly and actually measure the real world parts now I've got them, and try and work out how that's actually going to look. And then we can actually put the motor on there with a belt. Obviously there's no bracket, the hinges are floating in the air, so we do need to work out those details. So here are some of the physical parts. What we've got is an SFU 1605 ball screw, which is 16mm diameter and a 5mm pitch. And that's got end machining down to 10mm I think it is on this end, and it's got these bearing blocks that fit each end. So that's my 2060 extrusion, which makes up the thigh essentially, and these will be mounted of course sort of in there, and there's another one on the other side which operates the upper leg, and then we've got a motor which will be mounted like that, 2 of those, and that will run obviously down to here, so this will be on the piece of the ball screw there, and that'll be running a pulley like we did in the exosuit, and I'm probably going to attach this back to this block that's got holes in the top, the same as we did, exactly the same as before. So then we've got our knee joints, which sits there somewhere, and obviously the rod that comes across, and we want to make that perfect triangle so the maths is easy to sort out. So essentially we need to put a rod that goes from the middle of that into the middle of this. And with the exosuit we left this completely unsupported because the ball screw is pretty strong, and I think it is probably strong enough it won't bend the ball screw. But since I've got this 2060 V-slot here, what I really want is a little wheel that will run in that V-slot or 2 to help support this, and also want to stop this twisting. So the plan is going to be basically to use 2 of these V-wheels to go and run in those slots. So if we now lie this T-slot down, that basically means we've got to put this somehow like this and make a block that goes around this with these V-wheels mounted. So that means any pressure coming from the top here will be supported by the wheels, and because there's 2 of them that means this can't rotate and it can't twist the rods. Now I'm pretty sure the rods are going to be a pair of these, which are M10 studding with these M10 rod ends on. There is a slight disadvantage that this thing rotates around when it doesn't really need to, which is going to put some extra load on the thing that goes through it, because it'll allow it to twist as the rod pushes. So, and that thing of course needs to actually be attached to this. So there's a bit of thinking to do there. Some of these parts are eventually going to be CNC aluminium, but for now we're going to make 3D printed prototype parts. And of course I need to position this ball screw exactly right on my T-slot so that the wheels run correctly and everything lines up. So going from this rather basic sort of design that we've done here to this is now the detailed design with the ball screw mounted at the right dimensions. I've actually drawn the blocks the right size with the mounting holes in, the ball nut there with its again with its mounting screws in there, and so on. So this is a much more detailed version. You'll notice what I've got now is on the lower leg we've got this solid piece which looks like a 2040. The original plan was to use 2 2020s spaced out so the rods could go between. And I was originally going to use the end piece of that V-slot to run the wheel in, so the one on the edge out of the 3 But now in fact I've decided to run the wheels in both of those and put the ball screw in the middle. So that's resulted in the push rods being right on the outside there, and we can just put this together in one piece. So I may replace those 2020s with a single piece of 2040, but for now we'll use the 2020s for prototyping. So the main important thing about this, to do the trigonometry, was that the ball screw has to be perfectly in line with the pivot. And all of these points are pivoted in the middle here, so that makes a perfect triangle that's easy to solve. So there's two potential issues with that. One of course is that I do need to get the height of this ball screw right so the wheels run in the V properly, and that means this plate will need to be adjusted up and down, so the holes will be needed to be moved once I put it together to see if it actually works. And therefore we'll have to adjust this hole as well. So for now I've made these as separate plates so we can sort of fine tune them. Eventually there'll be one piece of aluminium which will be CNC'd out, and of course there's another motor on the other side, so this will in fact have an opposite piece with another joint to the other end. But for now we're going to 3D print them, so we'll make them separately, and that makes it easy to slide them up and down and get the spacing correct. The other issue is that of course we've got to put some sort of 10mm pivot in this hole, which isn't very deep. Eventually it could be aluminium and we could tap it and we could screw the 10mm in. For now it's going to be plastic, but that's only for prototyping. And the third issue is we've got to make a 10mm axle through the 2020 extrusion, and that means drilling a massive hole which is going to make a weak spot in the extrusion where it might snap. Of course we could put aluminium plates on either side and that would probably work okay, but we'll have to see how that looks in practice with the whole 30kg weight of the robot on its legs. Although it does have 4 legs, so it'll probably be alright. The other choice we've got of course is that we've got this gap here between this face and the rod, so we could actually kind of put this piece of 2040 in a cradle with the bearings mounted flush to the surface either side, have 10mm bearings there, and then this could actually be a piece of flat bar and we could stud weld on a piece of 10mm, so that makes a rigid right angle at each end, and again we could seat bearings into this block and that would allow us to keep that rod rigid. Just put bearings into a block here. We could probably even get away with a 3D printed piece of plastic, and that would be perfectly strong. We'd then have to of course hold these rods together with something in the middle. So for now I'm just going to drill the holes, put the 10mm studding in a piece of plastic, and we'll use the rod ends we've got for prototyping and checking the code and maths works. Alright, so I 3D printed that bracket that holds the motor, and that's attached with some T-nuts into the extrusion there, and I've 3D printed this part, and this has just got a hole through with the 2 wheels attached there. So if we take that out of there, that should run quite nicely up and down the V-slot. So as force pushes those push rods onto this piece, that'll be braced against the T-slot. That's the idea there. So this fits in here of course, and we've got some holes that line up to screw that on. So that all looks good so far. So we've got the bearing blocks of course, which then mount onto this red bracket, and they have to be perfectly in the right place. They also have to be spaced away from it and at the right height. So hopefully the holes are in the right place, but we need to put the blocks on each end and check these wheels still run properly. So I'm going to assemble that, and then we can deal with the shim that holds it away and something to support it underneath, because of course that leaves a gap. Right, so I've just used some nuts there as spacers to hold that, and that seems, it's not too bad actually for first go. There is a tiny bit of movement there, so those wheels aren't quite in the slots. Side to side it's okay, but they're basically a bit high, so I need to take sort of 1/2 mil off, move those holes down a little bit, and then I need to make a shim to replace those nuts that goes around there and comes in the bottom just to support it as well. So I've installed those blue shims there, which now hold these rigid. This is still a little bit loose unfortunately. I think before I couldn't really tell how far to move it because the plastic was bendy. Now it's quite rigid. I can see I probably need to go down another millimetre or something, but for now we're going to leave it like that. Obviously we need to change that in the future, and when that red plastic is rigid aluminium, it will make it much easier to see what's going on. You could just be able to make the holes slightly bigger or slots so I can sort of bed the thing right down when I fit it, and that gives me some leeway. But that'll do for now. Obviously the wheels rest in the grooves, it doesn't rotate, and we're only testing, so there's not too much load on it. So I've got a 3D printed T5 pulley on there, which was the same as the exosuit, only this one has a grub screw and the others were just push fit, so hopefully it won't come off. And that'll actually be what I'm going to use to start with. We may get some aluminium ones made, but that'll do for now. So I'm going to mount the motor, get that knee joint mounted at the other end, and put that rod in, and then we can actually test it. So I drilled a hole in my lower leg there for the 10mm studding to go through, but that has actually cut through most of the aluminium, so there's hardly anything left there for any strength. So I've made these plates that will go over side of the hole, and eventually they'll be CNC'd aluminium. For now it's a piece of plastic, but that'll do. So I've mounted my knee joint. It's mounted on bearings, you can see other side there, with that 10mm studding all the way through. The shaft is actually loose all the way through, which is a bit of an oversight, so it's got zip ties holding it on there. But we'll have to sort that out as well, so eventually it'll be fixed to one or the other. I might put the bearings actually in the joint and bolt it to the outside, or the bearings will be on the outside and we can put a nut on each side, something like that. And of course I've got those rods on that go between the nut here that goes up and down the ball screw and the leg. So obviously this is all metal. Eventually this will be metal, that plate will be metal, this will be metal, this will be metal. So eventually it's going to be pretty significant. It's actually pretty weighty already, and it's pretty solid of course. So the only concern really is where this 10mm tapped into the plastic, but that will be metal. So everything is going to be fine, and we've got quite a good range of motion. But if I take this up to one end, you can see in fact I run into a problem here where these start to touch the joint, and this hasn't got to the end, and that's why I've made this as a separate piece, so I can slide this up and we can get some more travel out of it at that end. Well, I tried to slide this way, but I actually can't do it because this bolt head hits this. So this would all have to be wider for that to work, or we'd have to take the bolt in the other way, tapped into aluminium when the red plate is metal. So for now I'm just going to leave it, and we'll pump the numbers into the code and everything should be fine. I've mounted the motor on there, which of course has a belt going onto the ball screw, and that's actually mounted on a 3D printed bracket, and the bracket is attached to studding and the bolts that go through all of this. So that makes it actually quite rigid. I need to put an encoder on the back end of the motor, and the motors are actually provided with these, which bolt onto the back. Now this is actually an M10 thread on here, and the encoder, the maximum size it will fit on, is an M8, so I could just turn this down in a lathe, although I don't have a lathe at the moment. So I've just made this 3D printed one with a bit of 8mm studding in. That's actually going to support the back of the motor as well as have the encoder mounted. So I've made this piece with a bearing in, and that slots on there, so that's just a normal skate sized bearing. And that screws onto the 2060, and that holds the back of the motor square and also gives me a mounting point for the encoder. So we've got the encoder on the back end here, so that's working okay. We've got our O drive hooked up again. Check out last time's video to find out more about the setup of that. And this now works of course, so if I hit some keys on my keyboard, I've just got the example sketch. Taking it from end to end there. So the motor's going pretty quick. I've actually tuned it up to 30 amps. It was set to 10, and I've tuned up the maximum speed as well. And I've had a go at those PID settings, so it seems to slow down quite well if you watch the motor without overshooting, which is quite good. So that seems pretty accurate. We've also got holding power on, of course, so if I turn it, it'll turn back, so there's absolutely no chance of back driving this mechanism. So that's looking pretty good. So some of the concerns in the comments from last time were that the ball screw and all of this might not be fast enough to make it actually walk. So I think this is pretty fast, judging by the speed of the actuators in Robot X and so on. If I just take it from end to end, that seems like it could be pretty slow, but if I do smaller motions, we can actually be quite agile there. The other thing to consider is, of course, we've actually got two actuators essentially stacked on top of each other, so when the bottom one bends to move the foot there, say it was picking the leg up, then of course the top one would bend as well there, and that means actually we get two actuators working stacked on top of each other at once, so the actual foot position would move twice as quick as a single actuator. On top of that, if the other three legs were, say, pushing back as this foot is travelling forwards, of course we get twice as much travel within the same time frame. So actually the end speed of the foot is actually going to end up sort of 4 times quicker than we can see in that single actuator. The other thing to consider is that this is getting on for around 4 kilograms once those pieces are made of metal. It's actually pretty heavy, mainly due to the motor and the ball screw. And we've still got to put the other ball screw on the motor on the back to make the actual hip joint, or whatever you want to call that, the upper leg joint. So this thing's going to be a tank basically. It's going to be able to exert quite a lot of force. If it's got rubbery, grippy feet, it's going to be able to push or pull a load, a bit like the Boston Dynamics Spot Mini where it pulls the door open, and it's going to be able to do all of those things. So these actuators, even though they're not really quick, they're going to be really agile, so it's going to be able to make some really strong, pragmatic moves, and it should still be able to walk perfectly well with small steps, moving each actuator a bit. So the next thing we need to do is try and drive this from the remote that we looked at last time and the code, to see if we can control that leg length and the actuator length and get it to track the controls. At the moment, I'm also only using this 6-cell LiPo pack, which is about 24 volts, and I've got the 24 volt version of the O drive. There is a 48 volt version available, so we could use 48 volts and run everything twice as quick, or even if I don't want to do that, I could run it at 36 volts or something, and I haven't purchased all of the O drives yet, so I could buy a complete set of 6 of the higher voltage versions. So let's talk about calibrating this for the remote. Last time we had some code where I could turn one stick and that gave me the desired leg length, and it worked out the trigonometry of all these angles to tell me the actuator length, at least from this angle, from the angle of the knee there. So basically what we've got here is an encoder on here which counts the position of the motor, and that's got 8,192 encoder counts per revolution. And we've got a 5mm ball screw, 5mm pitch. That means every resolution gives us 5mm of travel. So for 8,192 counts on this encoder, we'll travel 5mm linearly here. So to travel 100mm, so 100 divided by 5, and that gives us 20. So we need 20 revolutions to travel 100mm. So 8192 multiplied by 20 is 163,840. So we should be able to count 163,840 encoder counts, and that should move 100mm. But actually that's wrong, because we've got a reduction here on this belt, which is about, it's a funny number, it's about 2.14 something. So actually, having measured 100mm or measured some distance, counted the encoders and divided it and recalculated it, we actually need 349,000 exactly to get 100mm of travel. And that's just the travel of the actuator. What we'll actually need to do is add that to the distance to this joint to calibrate to the actual distance that we're calculating in trigonometry. Last time we did some code which took the rotary controller here, and basically that demanded the leg length, which is from the pivot there all the way up to the toe, and then basically it works out the actuator length for that. So we've still got that code here. And basically what I've done at the bottom here is basically taken off the 95mm, which is from the piece of the actuator to the joint there, because obviously it can't move there, so it's going to start at 95. We've constrained the actual actuator, so it's only 100mm of travel, so it doesn't run its end stops. We've basically said for every millimetre of travel, move the encoder 3,490 encoder clicks. And I'm also writing that out to the serial terminal, as you can see there. Now one thing I will say is this, the joysticks I've used here were £10 eBay specials, and you can see the numbers are jittering around quite a bit, and that's because there's a weird unsprung dead spot. So if I sort of turn it one way and leave it, I can get 77. If I turn it the other way and leave it, I can get 88 or 87. And basically, normally it should spring to the middle, but there's this kind of section of 10 in the middle where it doesn't spring properly, so the numbers tend to jitter around, and that's going to affect the actuator length, and that makes it look like the leg is jittering, but actually it's doing what it's supposed to. But we probably do need some motion smoothing on that. Alright, so now we've set up, we've actually patched that through, and we've put the code on, so we've got the Arduino Mega actually driving the O drive, so there's that jitter, and if I tap this joystick you can see it's pretty awful actually. But anyway, we'll actually track the stick, so obviously the motor's pretty torquey and it's going there and stopping immediately, so we do definitely need some motion smoothing, because otherwise it's shaking itself to pieces. But it is in fact tracking the motion there. So you should be able to see that I'm demanding a leg length there of around 710mm. The actuator's at 0, which is correct, and if I were to measure from the foot, which is missing, to this joint, we actually do have about 710mm. And obviously as I go up there making that leg length shorter, we can see the actuator length getting shorter. And if I could hold it in one position, we could measure it with a tape measure and actually check that that leg length is the right leg length and the actuator is correct. But I can assure you it is. And obviously we've hit the end stop. I've been a bit conservative there, but we could go a bit further and we could bend the leg further. Eventually I do want to have to move this ball screw up so that we can make use of that bit of dead patch, but again we had that issue with that bolt there we need to resolve in the design. So for now, that's about it. And where it's tipping over there is actually the torque of the rotary motor spinning the leg, so that's a pretty powerful motor. But yeah, definitely some motion smoothing to stop that jitter. One other thing we do definitely need is some sort of end switch at this end. So basically we'd have a home switch, and that means we could put the O drive into velocity mode, drive it really slowly towards the switch till it hits it, read the encoder position back in code on the Arduino, take that number away so we get 0, and that will give me the 0 encoder position every time. At the moment I have to manually roll the motor till I've got 95 mil on here, and then power it up, and that's the only way to 0 it. Right, good, so things work pretty much how I expected them to. Obviously we've come across a few issues with the design there, but that's really good, making this prototype out of 3D printed parts, so we can sort of sort that out before we cut metal. If I'd cut aluminium on the CNC machine right now, then we'd have wasted it basically. So pretty happy with what we've got, and I'm pretty happy with the functionality. Obviously we do need to do a lot more code for motion control and things like that, but that's all part of the fun. So this project is open source, and I am publishing the code in CAD as I go on GitHub, and you can find the link in the description below. So I need to explain for people who know about GitHub, I'm not using GitHub in the proper way at the moment. So what I'm doing is putting up folders called Part 1, Part 2, Part 3, which have got sort of different versions of the code in for each episode. Now it is possible on GitHub that people can submit code and I can merge that in, and it should be version tracked like that really, with one version with lots of different version control, so you can go back and see all the revisions. But for now I'm not doing that because I really want the point to understanding this to be really easy, so when someone clicks on the link they can go to part 1, they see the actual code, they don't have to go back through everyone's different pull requests and see what the updates have been. So eventually we will have one piece of code that people can put contributions onto, and I can test on the robot, and then we can go and put those on and say that's the final code, but that's going to be pretty much when the whole thing is together and working. So a few people have made pull requests, which is a submit of some change to the code. At the moment I haven't merged those in because I'm probably already working on the next episode, and I also know that you should really make your own GitHub repository and replicate that to your own machine and update that and work live on GitHub essentially, or with a replica of that repository, but I'm not doing that either. So for now the code should really be looked at as if it's code samples. It's really just me testing to see if things work the way I think they should. So for the moment I'm not really accepting contributions to that code. Eventually I'd love your contribution, but that's going to be a bit further down the line. So for now it's really published just for completeness and to show that the project is truly open source and it's licensed under GPL 3, which means that you can take it and you can sell it, or you can commercialize it or change it and commercialize it, but you must obviously then publish the changes to the source. So that's all very good, and that's all great for the community, and hopefully it'll be a great project that we can have lots of other people contributing to. So I'm also publishing the CAD for each episode. In the Part 1 folder we've got the basic overview of the dog. For the Part 2 folder on GitHub you'll find the CAD for this leg. So you can go and download that and make your own and make changes and make your own. You could go ahead and build the whole robot, although I don't recommend it. You should probably wait for me to do it unless you want to spin off your own project, in which case feel free to fork it, make your own changes and publish it and sell it if you can, and that's great and all part of the open source spirit. So there we go, that's pretty much the overview. So that's all for this video. Next time we're going to do a bit more hardware prototyping, probably a bit more code in electronics, and we're going to take the project forward like that, testing everything really with prototypes and doing the CAD and code, and then eventually building it. So don't forget to subscribe for more updates on this project and some of the other projects that are ongoing. It's also really important to say that this project and all my big builds, which aren't sponsored by a brand, are funded through Patreon. So have a look at patreon.com/xrobots, and basically that's funded by the community. So people are paying a small amount per video to get various rewards. So go and check that out and fund me if you'd like to, or if you don't want to, the project's still free and open source. Alright, that's all for now.